What is Dijkstra's algorithm and where can we use it? So let's dive deep into the details and see how it works. Let's start with a graph. Suppose in a graph we need to find distance between two vertices, initial and final, and this distance should be minimum in efforts to reach initial and final. There can be multiple paths in it, but we need to find the minimum one. Here we can find by our eyes, but what if the graph is a little complex? If multiple nodes are there and we need to find distance between two nodes, there can be multiple paths. We just cannot guess the path, so we need to apply an algorithm to find the best and minimum path. In this case, we use Dijkstra's algorithm to find the optimum path between initial and final node. Suppose that we have a graph and each edge has a weight associated with it which is positive and can mean anything like the actual distance between the nodes. And we need to travel from initial to final node and we need to find the minimum and optimum distance. So let's see how it works. First, we initialize the cost of every vertex to infinity because we are starting out and we don't know any distances. And then we will select a vertex, in this case the initial vertex, and we will adjust the cost of the adjacent vertices. In this case 5 and 2 because we will require 5 and 2 cost to reach there. So 5 and 2 are minimum and less than infinity, so we will change the nodes cost. And then we'll select the minimum cost vertex which is 2 and we will update the adjacent nodes cost to 5 because it will take us 2 to reach the selected node and 3 to reach the node we are updating the cost of. Again we select the minimum from the remaining, either one you can select. I'm selecting this, and let's adjust the adjacent nodes cost, which is 5 plus 2 and 5 plus 3 because it would take us 5 to reach the selected node and the edge to reach the adjacent nodes. So in this case 5 plus 2, 7 is less than infinity and 8 is not less than 5, so we'll update just this node. We select again from the remaining, in this case we'll select 5 because it's less than 7, and then we'll update the adjacent one if we can. So we'll check 5 plus 6 is not less than 7, so we will not update and we'll let it be 7, and let's select the final vertex and we are done. We've found the minimum cost to reach the final vertex from initial vertex. Now what about the path? To keep track of the path we need to update the cost and also write the name of the vertex from where we are coming. Don't worry, you'll see this in few seconds. Let's understand this with the same graph. In this case we'll focus on writing the name of the node we are coming from. In this case we're coming from A, so we'll label A in both of the nodes we're updating. And then we will select the minimum cost vertex which is 2A and we'll adjust the adjacent nodes. And we will update the label only if we are updating the cost. In this case we're coming from C, so we'll write 5C. But if you are not updating the cost, then let the label be what it was before. So here we are not changing the 5A because we are not changing the cost, but we will change the infinity to 7. So we will write the node's name we are coming from, which in this case is D. So 7D it will be. And hence, as you can see, the path will be A, C, D, E. We'll track E, D, D, C, C, A. So in this manner, we'll backtrack the path finally. Let us now see the time complexity of the algorithm. For that we need to see how algorithm works. So the algorithm checks n nodes, and from each node it checks n maximum adjacent nodes, which gives us O of n times n, which is O of n squared, which is quadratic time complexity. Now let's see the disadvantages of the algorithm. The major disadvantage of the algorithm is the blind search. In blind search, we go on searching the unnecessary nodes for the path. So instead of going forward, we go backward sometimes and waste time and resources in this algorithm. So that's it for this video. I hope you liked it. Consider subscribing Code Snack channel for such explanation videos. Thanks for watching.